Okay, so this section is the beginning of a new chapter. It's obviously leading us into what we're doing for the rest of the chapter. This chapter is going to very quickly turn into a lot of visualization stuff, okay? So if you're a visual person, you're probably going to like it, and if you're not, you may not. We're all going to work with it together, and this section is very much an intro kind of a section. So I do think that it's going to revolve a lot around things you've seen before and just tweak a little bit more than what we've seen. So the basic idea of what we're going to be doing in this lesson is we're going to be taking graphs, general graphs, and we're going to be finding area between them. Now, all the areas that we have found so far back in Calc 1 have been finding the area from a graph down to where? Where does the area go all the way back down to? The x-axis, right? We shaded from whatever the graph was all the way back down to the x-axis. Now, if you can imagine this graph and we want to find the green area, right? Well, if we ignored the shading that's here and we took our graph of f of x and we shaded it all the way back down to the x-axis, and then we took the graph of g of x and we shaded it down to the x-axis, how would we find that trapped green area? Yeah, you just subtract those two areas, right? So from what we've done before, it would look something like this. They are calling that A and B. So this is A and B, and we're taking the area of f of x because that's the top one, right? And we're subtracting dx. Subtracting off the area from A to B of g of x dx. And that would give us the trapped green area. But one of our properties of integrals said that instead of doing these two separate integrals, we also could write it slightly differently and say, okay, well, this is the same thing as doing f of x minus g of x and then integrating it, right? So if we had the ability to subtract our functions themselves and they collapsed somehow nicely, it might be easier to do the antiderivative afterwards. But sometimes we just put them together and we do them separately anyway. So, okay, does that all make sense? Okay, so that's what we're going to be doing. We're looking for this trapped area. Now, some of the graphs look like this, where they're going to tell us where we're going to start and where we're going to stop. Some of the graphs are going to look a little differently. So on this one, first, we're not going to actually do the whole process. We're just working with the graph part of it on this one. So, number one, we're going to sketch the graph corresponding to the following integral and shade the area. Right? So we're just doing a picture on this one. We're not actually doing the calculus part of it. We're doing the picture part of it. We'll do the calculus part of it on the next one. So this one has merged them together, much like this last piece here has been merged together into a single integral. So what it's asking us to do, though, is sort of if I were separating these back out, what would they look like? In other words, this one goes from -1 to 1 of 2 minus x squared. That's the first piece. And I'm subtracting off the -1 to 1 of x squared. And that's my second piece. Okay, so I'm just breaking them apart, kind of decomposing them instead of pushing them together. And we're going to take a look at the graph. So go ahead and get your calculator out. Where'd mine go? And we're going to put this first piece here into y1. Looks like a g. Let's try again. And we're going to put this second function, it's just x squared, into y2. And we want our graph to go from -1 to 1. If you want to make it a little bit bigger, just to give yourself some sort of buffer perspective on the side, like maybe from -2 to -2 to 2, that would be reasonable. So in y1, I've got 2 minus x squared. And in y2, I have x squared. I'm going to make my window go from -2 to 2. And you can play with the y-axis if you want on your own, or if you'll remember, we talked before about hitting the zoom 0, which is zoom fit, and it puts it into its own window that's supposed to be a good window for the x value you've chosen. And it shouldn't come as any surprise to you what pulls up. It's a parabola, one of them opening upward and one of them opening downward. Okay, so my graph looks something like this. And I don't need it to be perfect. I'm just going to have a sketch here. That's actually pretty decent. And if you trace or if you go to where these graphs are intersecting, you'll see pretty quickly that it happens to be that they intersect at the -1 and the 1 that are actually the lower and the upper limits of integration that we were given. Now, they don't have to be those numbers. They just happen to be those numbers here. Okay, did everybody get this graph? It looks like that, all right? And so the shaded in area between these two curves is right here, this sort of football-looking kind of shape in between. Because that's the indicated area that they're talking about. Now, on this one, obviously, the original way that the problem was set up, it would be easier to just do the simplification of those two functions and then integrate. But it wouldn't be hard to do the integrations and then to evaluate them either, because none of these are difficult functions to integrate. Okay, so the picture makes sense. All right? So let's take a look at this one then. This one starts out a little bit differently, actually quite a bit differently for various reasons. So can you tell me something that you notice about this one that's different? It's in y's. That's the biggest difference right there. And it's not just like they changed x to y and it didn't really matter. It matters. The y here is really the y that we're talking about on our xy coordinate plane. So that's going to be a difference. You might also notice that it's not actually set up for you as an integral, right? True? In addition to that, you might notice that it doesn't give you like the -1 and the 1 or the a and the b that the last two problems have referenced, does it? Okay, so there's actually quite a few differences here. The biggest one being the y, which you guys noticed right off, so it's really good. But the other ones are also nuances that can happen even if they'd been in terms of x. So what we're going to do is we're going to start with actually drawing this out. And unfortunately, our calculator is not all that useful because our calculator only lets us put functions in terms of y equals. And these are basically x equals equations, right? So in a very real sense, you actually have here, whoops, my pen, x equals y squared and x equals y plus 2. Now the x equals y plus 2 is not so bad. We could solve this for y and we could draw the graph from there. But this other one ends up being not a function at all. So we're going to draw this by hand because it's in terms of y. So if I had had the equation y equal x squared, it would be a parabola opening upward, correct? Do you remember what the graph of x equal y squared should look like? What is it, Adrian?
Should it be to the side?
Yeah. So it'll still be a parabola, right?
Yeah.
But it'll be opening to the side. Which side? The right side or the left side? Do you know? The right side. Yeah. So this one will actually be a parabola opening, whoops, like this. So this is our first equation. I'll label it as f of y, like they have before. If you're struggling and you're like, how did they get that? I don't remember, or how would I know? You can also think about what would happen if you tried to solve this for y. If I actually tried to solve this for y, I take a square root. But when you take a square root, right, you'd get like the square root of x. But you'd actually get a plus or a minus. So the top part is the square root of x graph. So this graph up here is the square root of x. The bottom part is the negative square root of x graph. So you can think about that from that perspective too, if that's helpful. The other equation, we could solve for y pretty easily, and it works really nicely. So this is y equals x minus 2. So it has an x-intercept, sorry, we'll start with y-intercept, has a y-intercept of 2. That's negative, so down here, something like that. And then it would also have an x-intercept of 2. So my picture's not drawn to scale very well, but we can still, I think, kind of make do with it. So we have these ordered pairs, and then we're going to draw the line that's going to connect them. Okay, is that all right? Now, notice how the directions are worded. They say bounded area. Now, this one happened to be bounded area as well, but we didn't really have to care about what the -1 and the 1 bounds were because they told us. Here they don't tell us. We actually need to know what is bounding this area. So shaded in wise, if you will, it's this piece. And you can see where it's being bounded. It's whatever these two locations are right here. But we're not told what they are, correct? So we need to know what those values are, and we can do that with algebra by looking at the equations that we were given. We want those equations to be equal. So we're going to set them equal to one another. So we have y squared and y plus 2. And we need to figure out where these are equal. How do I solve an equation like that?
You just subtract the y.
Okay, so I'm going to eventually want to factor. If it does, if it didn't factor, what would I have to do potentially? Quadratic formula or completing the square. But in order to do any of that, Levi, what am I going to do first?
Subtract the y.
Yeah, and not just the y, but the 2 as well. So everything needs to move on to the same side to be able to do any of the methods that we've mentioned. So my very first step is to change this into y squared minus y minus 2 equals 0. Now, this one is very friendly, and I don't want to say that all of them will be, but a lot of them are when they give them to you, and they are able to do things like factor. So that's kind of a common occurrence in the problems that show up. So don't be surprised if that happens, but they don't all have to, of course. So if I factor this, what will I get?
Y minus 2.
Y minus 2, y minus, or y plus 1, which means what are my y values where this happens? Yep, 2 and negative 1. So over here, this is not drawn exactly very well, but this is happening right here at negative 1. And up here, it's crossing at 2. And they're y values, so I've listed them on the y-axis, right? Not on the x-axis. Okay, so now when we had these graphs over here, what we said we wanted to do is we wanted to take the top graph and subtract the bottom graph. Okay, so what do you think we might do here? Same. Okay, so if I write this down, what would be my top graph? Okay, the y squared, and then minus the y plus 2. Okay, my limits of integration for y, we just found the lower one was negative 1, the upper one was 2, and we will have the dy on the end because my variable is y, right? Not dx, but dy. Okay, is everybody good? So far, so good. Okay, so we need to integrate this. This is simple polynomial kind of integration. We can do this pretty quick. What's the integral of y squared? Yep, 1/3, I'll even write it that way, 1/3 y cubed, or y cubed over 3. This is subtraction, so it's going to distribute the negative through. So I have negative y, which would be 1/2 y squared, and then negative 2y. And this is being evaluated at 2 and negative 1. So I'm gonna write it out as putting the number 2 and the number negative 1 in. So I have 2 cubed minus 1/2, 2 squared minus 2 times 2. And then 1/3 negative 1 cubed minus 1/2. Okay, I'm running out of space. Let me move it. Negative 1 squared minus 2 times negative 1. And you're welcome to let your calculator kind of do some of the computations. These aren't terrible, so I'll just do them by hand. But I have 2 cubed, which is 8 over 3, so this one's 8/3. I have 2 squared, which is 4 over 2, so that's minus 2. And then I have minus 2 times 2, which is minus 4. So that's the first piece. Second piece, I have negative 1 cubed, which would still be negative 1, so I have negative 1/3. And then I have negative 1 squared, which would be 1, and my 1/2, so I have negative 1/2. And then I have minus a negative 2, so that's plus 2 here. Let's see. So I'm kind of done with evaluation, so let's write this down. On the first one, I have 8/3 minus 6, which is negative 10/3. And on the second one, I have negative 1/3 minus 1/2, hang on, and plus 2. So this is minus 7/6. And if I take negative 10/3 minus 7/6, yeah, I have negative 9/2 or negative 4.5 if you prefer. It's fine. But it's negative. Okay, so think back to Calc 1. Back to Calc 1, not what we're doing right now at all. When we got negative areas, what did it mean?
It was below the y-axis, right?
Right, x. It was below the x-axis. Yeah. Okay, so when we had negative areas, it meant that it was below the x-axis. So what do you think would happen, or what do you think from the perspective of these graphs? How am I going to get a negative area if I'm using trapped areas? What would have happened?
Everything under the curve cancels out everything over the curve, and that cancels out there's negative in the curve.
Okay, but I'm not under the curve with this graph at all.
No.
Tanner, what are you thinking?
I was just going to say what we consider the top curve and the bottom curve. But I mean, we just do that by looking at the graphs.
Okay, but you're on the right track, Tanner. So on this graph, this specific one right here, if I were to have subtracted g minus x, I'd get negative area, correct? Because it would have taken this small little piece here at the bottom that's represented in white, and it would have subtracted from the top all the way down to that. I would have still gotten the green piece, but I would have had the wrong sign. Agreed? So if I subtract the wrong one, like the order, if the order is wrong, I end up getting a negative area. So what do you think that we did over here when we did this? I mean, we did it wrong.
Oh, it's because it's the y.
Oh, there we go. Okay, so we did it wrong on purpose. Because I'm hoping that this will remind you when you do it later on that if this happens again, you can sort of trigger, wait a minute, what did we do when we did it wrong? This is supposed to be the value that's bigger in the y-axis, not the x-axis. So if you take a look at these graphs, right, the one that I've drawn sort of the parabola in black and then the line in red, and you're thinking about it from the perspective of, tilting your head sideways on the y-axis, right, like this, the graph that's actually to the right-hand side is the larger x values. We did our subtraction backwards because we were considering it from the top down instead of from the right to the left, weren't we? Okay. But don't we really get just the same value, just the wrong sign? We do, yeah? So an option, instead of worrying each time about which one's on the top and which one's on the bottom, which one's to the right and which one's to the left, is we could just do something else. Absolute values. So another option here, instead of worrying about which one's on the top and which one's on the bottom, is that we could do this, and we could just do absolute values of what we have instead. You don't have to. You can pay attention closely and make sure you get the subtraction in the right order. And if you do it wrong, you can always switch it. There's nothing wrong with that. It's just an alternate point of view. And because we've already done this problem, and we've done it with the wrong direction, I don't want to redo it in the right direction at this point. That doesn't seem like a very good use of my time. So instead of doing it that way, what we can do is we can go back up to the beginning and we can put absolute values in everywhere. I shouldn't have done it quite like that. Sorry, one more step. I got too many absolute values going on. I want the absolute value around the whole thing. That's where I want it, like this. That's what I want. So when I take the absolute value here, there's the positive 4.5 that I really should have had instead of the negative 4.5. Does that make sense? Okay. So just because you get a negative at the end doesn't mean you really did it wrong. You just need to go back and make sure that you've got your absolute values in there if you want to do it that way. Yep, Jackson.
Couldn't you solve that problem
on the x-axis if you use the equations that we solved for y?
So you could if you had functions. The problem right here is that we would have to actually have the the x value defined in two different ways over here, like this. I said it right the first time. The y value defined in two different ways. And it would either be the absolute value of x, or, not absolute value, the square root of x, or the negative square root of x. And so if you think about this perspective right here, well, actually, let me draw something in here that we have seen before, but we haven't done it yet this semester. So you remember we looked at rectangles. Do you remember that? And our rectangles were vertical rectangles here, okay? So when we looked at this, we just made a whole bunch of rectangles in between, and we found their individual areas. And as soon as we stopped doing that, you were much happier, weren't you? Yes. Well, we're going to come back to this idea of these rectangles later on in section 7.2, actually. You can see the rectangles are here. What's happening on this graph, though, is that the rectangles don't look like that. What do they look like? They look like tilted down on their side rectangles. So the rectangles over here, if we were to draw them, look like this. And so for sort of the top half of this graph, that is the graph part that's above the x-axis, we'd have one definition for what the value is for the graph that we're subtracting, right? This would be this graph, the red piece, and then we'd subtract off the square root of x. But as soon as we shift to being below the x-axis, we'd have a different definition for what the y that we're subtracting, namely it would be negative square root of x, is. And so because we have two different definitions for what we're subtracting, it makes it more complicated to change it and to do it in terms of x. Does that make sense, Jackson?
Yeah.
Okay, so I'm glad you asked that, because that's exactly what we're going to see happen and have to make decisions about when we move into 7.2 and beyond, is which graph is actually going to change and be easier to work with in terms of x or in terms of y. And the answer is sometimes we have choices and we can pick either one. And sometimes we don't, and we really have to pick a specific value. Here, it becomes much more difficult if we switch it in terms of x. Okay? All right, let's take a look at another one. How is this one different than the ones we've done before? It's trig. That's one reason. It has a bounded x-axis. It actually tells us the bounds, right? It starts from negative pi thirds to pi thirds. The last one it didn't tell us. And for the third thing that is different about it, I want you to graph it, because you can't know probably until you do. So I'd like for you to graph it, and I'd like for the graph really to say negative pi thirds to pi thirds. So in y1, you're going to put this one, and in y2, you're going to put the tangent. In case you've been sharing a calculator with someone else or somebody's used it for trig recently, make sure your mode is in radian mode. Make sure your window then goes from negative pi over 3 to pi over 3. And then you can do this zoom fit, and it'll work really well on this one, I think. Okay. From the graph, what's different about this one? Say it again, Sophia. There's two separate pieces, right? And so another way of saying that is that the graph sort of overlaps itself. We didn't have that happen before. It closed things in, or it didn't, but it didn't overlap itself. So let me sketch what the graph looks like on mine, and you can confirm if yours does too. And again, we're looking for something that's pretty close to what we're seeing. Looks something like that. This looks like those pods from the trees that fly down and they twirl. That's what it looks like to me. The twirly pod things, you know what I'm talking about? That's what it looks like. Now, this graph has some symmetry, right? And this bottom sort of propeller shape is the same piece as this one right here. All right. I'm going to do this like it doesn't have the symmetry. The reason I'm going to do that is because not all graphs will. On this one, obviously, we could just find like this piece and just double it. And that would be totally acceptable. There's nothing wrong with that for this graph. But there's going to be graphs you're going to encounter that don't have symmetry, and we would want to see how we would do those differently, okay? So here's what we're going to do. We're going to do two separate integrals. One of the integrals will start at this negative pi thirds, which happens to be the exact value, right, that they're crossing over there. If it weren't, you'd have to figure out what the value was. Like if it doesn't give you the negative pi thirds and just says bounded area or something, you have to figure out what those are. You can see pretty quickly where they're crossing here in the middle, right? It's at 0. And then the upper end over here, same thing. We're at pi thirds. Whoops. So one of our integrals is going to say the integral from negative pi thirds to 0. And then the other one is going to say the integral from 0 to pi over 3. Right? All right. We didn't pay particular attention to which one. Well, we did. We thought we did it right? We were looking at which one was on top and bottom, and we worked with absolute values when it didn't, and so forth. And you can do the absolute values here again if you wish. They're kind of messy on the front end to put them in. So let's take just a second and identify which one's really on top of each of these. So as this graphed, the first graph was the sine graph, right? You put sine in 1, and the sine graph was the one that started out, I'll highlight mine in green, down here and went up here. That was the sine graph, wasn't it? I'm pretty sure that that's how I saw mine graph. Yeah? Okay, good. So on the left-hand side, it's the tangent graph that's on top, right? And on the right-hand side, it's the sine graph that's on top. So in terms of writing this out, we have tangent of x minus 2 sine of x on the top part. Well, the way I've written it in, the first part anyway. And then we would reverse it for the second part. Now we would have 2 sine of x minus tangent of x for this one. Again, if you want to use absolute values, you can do that. I just wanted to show another one where we actually pay attention to it. Sometimes people don't like the absolute values. They look a little bit weird. And sometimes people will just put the absolute values in at the end when they find they needed them to begin with. And you can do that too. There's nothing about that that's wrong. I'm going to switch this to the next screen so I have some more space to work. Okay, so these are our integrals that we're going to find. This is why I asked you to get out your sheet, is because you probably remember just fine what the antiderivative of sine is, but you might not remember just fine what the antiderivative of tangent is at the moment. So take a look real quick. What is the antiderivative of tangent? What is it? Huh? That's the derivative. Yeah, everybody remembers the derivative one, yeah.
Negative element of cosine.
Negative the natural log of the cosine of x and the, it's the absolute value of cosine of x, right? And then we don't need the plus c because we've got limits of integration. That's our antiderivative for tangent. What's our antiderivative for sine, 2 sine x? Yeah, we would change the sign, so it would be positive, ended up being positive, right? Positive 2 cosine of x. All of that needs to be evaluated from 0 down to negative pi thirds. And then we've got the same thing happening on the second piece, but reversed. So I now have negative 2, it is the opposite sign, so it's negative 2 sine of x. And then I will have the opposite sign for the tangent as well, so it's plus the natural log of the absolute value of cosine of x. And these are evaluated.
Wouldn't it be
Oops.
negative 2 cosine x?
Sorry, yes, thank you. Okay. Everything else is okay?
Well, wouldn't you be subtracting the 2 since you're evaluating them?
Which one are you talking about, Adrian?
The total of 1 on the left and on the right. Wouldn't you subtract that? Oh, never mind, they're adding.
We're adding, yeah, we're adding because we have these 2 separate pieces. And to be honest, we recognize, right, that whatever I get in this first bracket, it's going to equal the same thing as the second bracket. And if we did happen to have put our subtraction in the wrong order, we're just going to get negatives. We didn't, so we're not, but we would have gotten negatives and we would just switch them as well. Okay, This is pi thirds and 0. Okay, so we're going to do a little bit of trig, unit circle kind of stuff. So turn that trig part of your brain on. We've got some logs going on here as well, so we'll be a little bit careful. But we have the negative natural log. So we're going to put in the value 0 first. What's the cosine of 0? 1. So I don't really need the absolute value. I'm just going to write that as negative natural log of 1 plus 2. And I need the cosine of 0, which we already said was a 1. So this is what we get when we evaluate this out 0. Now we're going to evaluate this at pi thirds. Okay, so what's the cosine? I'm sorry, negative pi thirds. What is the cosine of negative pi over 3? Might have to draw that one out because we're also looking at negatives. Let me circle. Where's negative pi thirds? What quadrant is it in? Let's start with that. It's in quadrant 4. Okay, good. So we're in quadrant 4. That's what I was meaning by where. And it's the one that's closest to the y-axis. That didn't work well at all. It's still not working well. All right. It could be better, but that's not too bad. It's down here, right? What's the cosine value at this point? It's positive 1/2. It's still the x value, and we're on the right-hand side. So the cosine value at this location is 1/2. Everybody good with that? Okay. If you're not sure, you can also, on this one, because it's 1/2, it works really nicely to type it in your calculator. Just type in cosine of negative pi over 3. It's going to spec out you 1/2. So this is actually the value 1/2 here. So I've got negative natural log of 1/2 inside that bracket. And then I have plus 2, and it's times another 1/2. Okay, is that all right? All right, I need to move this down because I need a little more space. We're going to evaluate this at the same pi thirds, but now it's the positive pi thirds, which means I'm up here, right? What's the cosine value when I'm at positive pi thirds? It's 1/2 again, right? Because we're still on the right-hand side of the graph for the x values. So I have negative 2, and I have 1/2, and then plus the natural log of the cosine of the cosine of pi over thirds, which is another 1/2. And I have all of that minus what happens when I plug in 0. So when I plug in 0, I have the same things I had before. So negative 2 times 1, because the cosine of 0 is 1, and then plus the natural log of 1. Okay, did I get all those pieces in there okay? Yes.
You have 2 natural log of 1/2 there. Where did you get that? Where did the 3 come from?
It shouldn't be there. I was using something else. Yep. Okay. Anything else I've got? It's an error. Good catches, good catches. Okay, are we good now? What's the natural log of 1/2? I didn't say that right. I wanted to ask you what's the natural log of 1. That's what I meant to ask, sorry. What's the natural log of 1?
0.
That one's 0. So all of these, all these that are natural log of 1s are 0. So that's here and here. And then we've got some pieces. So I have 2 minus a negative, so plus the natural log of 1/2. And then I have plus a 1. Minus a 1, because I have the negative that's in front here applying to this, right? And then on the other side, I have minus another 2, because I have 2 times 1/2. I have plus the natural log of 1/2. And then I have, goodness gracious, I have minus a negative, so I have plus. And it's 2 times 1/2, 2 times 1, so I have a 2. Nope, something's wrong. Where's my 1? This one's a 1.
Yep.
Okay. These should be matching these, are they? Yeah, every single one matches, doesn't they? Yep, okay. So if I add the corresponding pieces together, we'll just do the first piece. I have a 2, I have a minus 1, so this is 1 plus natural log of 1/2.
Wait, hold on. Wouldn't the 2 times 1/2, that is equal 1? At the end there.
The 2 times 1/2 right here did equal 1, and it's right here.
Oh, okay.
Yeah, and the same thing happened right here, and it's the one right here. So yes, that's the one I missed earlier, in fact, yeah. And then over here I have 1 plus the natural log of 1/2. So the total here is what?
Two plus natural log of 1/4.
Okay, so 2 plus, I'm going to write it differently first. 2 plus 2 natural log of 1/2. Or, Preston, was that you? No, Pierce, who said it? Preston, okay. Or you can write that, you're exactly right, as 2 plus the natural log of 1/4. It's 1/4 because we can take that 2 that's in the front and we can make it a square. Okay, so there's no way for your calculator to give you this answer, right? Your calculator will not spit back out at you an answer in terms of natural logs. So these are the exact answer, but I'd like to remind you about how you can use your calculator to get approximations. Do you want to give it a shot? Okay, it's been a while since we've done it, so let's try it again too. You've already got the 2 sine x and the 2 tangent, or in the tangent of x in your calculator, but let's put them on the same line. So let's just make it to say 2 sine x minus tangent x. Okay, so y1 is now saying 2 sine x minus tangent x. Does it say that? Okay, and I don't care whether we go from negative pi thirds to 0 or 0 to pi thirds. It doesn't matter. We're going to do one or the other. Okay, so let's just graph this where it is right now. And we're probably going to go from 0 to pi thirds because it'll give us, so the graph actually looks kind of like a sine on your total curve anyway. Does yours look like that? Looks something like this. Okay, we're going to go from 0 to pi thirds because it doesn't really matter anyway. So if you go back to your regular screen, there's 2 different ways to do this. We'll do it in the regular screen first. One of them is Math 9. So if you hit Math 9, my calculator shows up and says F and INT, but I don't think any of yours does. Does any of yours say F and INT? 2 of them do. Okay. So if it says F and INT, what you do next is you tell it y1, comma, x, comma, and then you do your lower and upper limits of integration. So 0 and pi thirds. Okay, so we get the y1, remember, underneath vars, y vars, function, and y1. That's where that comes from. Sophia, I'm going to borrow your calculator if you don't mind for just a second. Just remind yourself how it looks. Thank you. If you do the other one, if you have the other version, your calculator actually ends up looking like this when you start out. And it has some boxes. I'll put the boxes in red. It has a box here, a box here, a box here. It has a D, and then it has a box here. Did I get that written right? I'm sorry, I hit a button for yours, so it says H now. So if yours looks like this, you fill in these values with the same things that are in my parentheses afterwards. It just looks a little bit more like what it's actually showing up as. This one we put in a 0. This one we would put in a pi over 3. In the middle here you put y1, and you get y1 the same way by hitting vars, y vars, function y1, and then you put the dx at the end. Okay, this is not going to give us a natural log kind of answer, but we can still check our work by using it. Okay, so if you do this, let me do it too. My calculator says 0.30685. Did yours say that too? Okay, so this is approximately. Go with that for now. 685, it looks something like this. And of course, that's half of my graph. So if I hit times 2 to double it, I'd get about, so doubled. I have 0.613705, whatever. If you take the answer that we got, which was 2 plus either 2 natural log 1/2 or natural log of 1/4, and you press, you typed that in, type in the exact answer that we got down here in one of these boxes, one of these 2 versions of it, it will give you the same decimal approximation that we just got by using this. Let me remind you one more thing, just because there's one more way you can do this that's a little bit more visual and it's fun, and we have just a second to do it anyway. If you go back to your window and you graph it, and you see this picture, and instead of doing it from where we did before, you can hit second trace, which is the calc menu. Option number 7 looks like an integral, so you choose number 7. You tell it the lower limit's 0. Your upper limit is pi over 3. Okay, mine just gave me an error. Did yours give you an error?
Yes.
Okay,
I
why
think it's
did-
because that's the end of the function.
Is my window's not quite big enough? Is that what you're
Yeah.
thinking? Let me make my window a little bigger. You may be right. Because it has to do it just a little bit off pi over 3. The window has to actually include all your values, and it may be that it's doing a decimal approximation just enough that it's not working, so let's try that. I just made my window a tiny bit bigger. We're going to do it again. So second calc, number 7, lower limit 0, upper limit pi over 3. Yes, it worked. Good call, Piers. And it tells me at the bottom 0.30685,282, which is what we got from the other view. So you can see it from the picture point of view this way too. All right, one thing I want to make note of for just a second. You have to graph this. If you had not graphed this, and you didn't realize that it crossed over itself in the middle at 0, what answer would you get if you had started at negative pi over 3 and ended at pi over 3?
0.
0. You would have got an answer of 0, right? Because on one piece, it would have calculated the subtraction of the top minus the bottom, and the other piece would have been the bottom minus top, because we would have had to put them in some order, right? One order or the other. And we would have gotten an answer of 0. But we shouldn't be getting an answer of 0. We have to take a look at the graph to know that there's any possibility of where they cross in the middle. That's an important step in the process. Okay? All right.